Good day. The lesson for today is to continue our discussion of linkages as they work in mechanisms. Now, the last time we were discussing the linkages as they are for the slider crank mechanism, and we were trying to determine the stroke, which is the distance in which the slider moves in one revolution. Now today what I want to do is to determine what the lengths of the links are, L2 and L3, because it's these two lengths that determine the stroke. So in design, you may be required to do one or the other. You may be required to say, we must have a specific stroke, so determine the lengths of the links, or you may have these lengths and they want to know what the stroke is. So I'm taking another approach to the same problem of the crank slider. Now again, basically we're using trigonometry and just trying to apply the basic principles of, in this case here, of the Pythagorean theorem. Now this is how it works. We have these dotted lines that represents L2 and L3 in the two positions. The one is the extended position, and the other is the overlap position. So now once we have that, we can determine what the stroke is, and then we'll be given L4 and L4 prime, and we'll need to find L2 and L3. So this is basically just another approach to these kinds of mechanisms. As I said before, these are the most common mechanisms that you'll find, or linkages that you'll find. Now, so what I'm going to do is express what the length of the two links together when they're extended. This is what I want to find. I want to find when L3 and L2 are together and they're extended, what would that distance be? And I'm going to call that x. So the sum of L3 and L2 is going to be called x. And then I use the Pythagorean theorem here. L1 squared plus L2 squared, or L4 squared, excuse me, will determine that length. So now I know how long it is when it goes all the way out. Now the second step is to look at the mechanism when the links are overlapped. And that would be L3 minus L2, and I'm going to call that x prime. So then I use the same formula again, except this time I'm going to include here L4 prime, because there's two positions. L4 is all the way out and L4 prime is all the way back. So once I've done that, then I'll have another length, and that's going to be called x prime. So I have x and I have x prime. Now that I have the two end positions, they're called the limiting positions, then I can just subtract one from the other and divide by 2, and I'll be able to find L2. So then once L2 is discovered, then all I need to do is to take x and subtract L2 from it, and that will get me L3. So it's basically just using the Pythagorean theorem, understanding that we have two positions here that we're going to use, and that'll help us determine then exactly what the lengths are of those in that linkage. So that's basically just a reverse of what we had done before. Now to continue, the other example that we have is the crank rocker. Now in this case here, in this situation, the last time we were here, we discovered what the displacement was of the rocker. So we found that angle, and that was the stroke S. Now I'm going to give you the stroke S and give you an angle theta that is from the link 4 to link 1, and then we can determine what the lengths of these two links are. This is L2 and this is L3. So we're going to find out what L2 and L3 is in order to accomplish a specific stroke angle. And to do that, it's very simple and very similar to this process, except because the way the linkage is set up, we have a 4-bar link, and we cannot use Pythagorean because we don't have a right triangle in this situation. So we're going to end up with two oblique triangles, and therefore we're going to have to revert to the law of cosines. So we use the law of cosines in the same vein as we did over here. So again, we start out with, as I said, as I did last time, we have L2 plus L3 is going to equal L1 squared plus L4 squared minus L1, L4 cosine of theta. Now the theta is, as you can see in my diagram, the angle from L1 to L4. It's this angle. In other words, the line that connects between those two pivot points is L1. Once we've discovered that, then I know what the angle is for theta, which is the extended, when these two links are extended. And the second step is to find what the length of the overlap, and this is L3 minus L2. Proceeding the same way as I did before, I can discover what this theta prime angle will be, and then I'll be able, or discover what the length of that angle is, and I'll be able to discover that angle. Okay? Now, to find L2, then I'll use almost the same. As a matter of fact, it is exactly the same as I did over in the last problem. This is x minus x prime divided by 2, and this is L3 equals x minus L2. So basically now I've been able to discover the link lengths in order to get the specific angle I want, and the link lengths for a slider when I know what the stroke is, or when I know what either one of these L4s or L4 prime is. So that's another engineering possibility, and as you get into your engineering field, you may run into this. All right, so this summarizes another approach to the crank rocker and the crank slider. Okay? Very good. Thank you very much.